In this video, we look at how computers store real numbers, or fractions. Firstly, let's remind ourselves how computers store integers. Consider this number line. Here we're using 8 bits to store a number to keep the illustration simple. We note how the place values double as you move from right to left, 1, 2, 4, 8, 16, etc. Note the most significant bit always represents a negative number, using 2's complement. So the number 6 would be represented as 0, 0, 0, 0, 0, 1, 1, 0. Now in order to store 6.5, we need to extend the number line from left to right, like this. Notice how the place values halve as you move left to right, a half, a quarter, an eighth, and so on. We can place a binary point between 1 and a half. So the number 6.5 is 0, 0, 1, 1, 0, 1, 0, 0. So let's look at another example, 3.75. So 3.75 is 0, 0, 0, 1, 1, 1, 1, 0. So that is 2 plus 1 plus a half plus a quarter equals 3.75. Now let's look at one more example, minus 6.5. Now because this is a negative number, the most significant bit must be a 1. So 1 minus 16, 1, 8, no 4's, no 2's, a 1 and a half. So that is minus 16 plus 8 plus 1 plus a half, which equals minus 6.5. This method of storing fractions is known as fixed point binary because the position of the point is fixed on the number line. You'll notice that the range of numbers that we can store is limited because some have to be used to store the fractional part of the number. So the biggest positive number that we could store with these 8 bits is now 0, 1, 1, 1, 1, 1, 1, 1. And that is much less than if we weren't using these 3 bits to store a fractional component. And this is a bit of a problem. You may also realise that some numbers can't be stored accurately at all. So for example, a third is going to be 0, 0, 0, 0, 0, 0, 1, 0. And that's actually a recurring pattern, so it would be 1, 0, 1, 0, 1, 0, 1, 0. But we can't exactly store a third given the number of bits that we have. So to increase accuracy, we need to change the way we use the binary point. Consider this illustration, where although we're still using 8 bits to store a number, represented in red, the 8 bits on the number line change. Or to see it another way, the binary point is floating up and down the number line. So in the first example, we've got minus 8 down to 1/16. Still 8 bits, but the binary point is allowing 4 bits to the left and 4 bits to the right. Now in the second example, we're going from minus 64 to a half. And in this illustration, we're only using 1 bit to the right to represent the fractional component. So the size of the number has increased, but the accuracy of it has decreased. And in the final example, we're going from minus 4 to 1/32, or 3 bits to the left and 5 bits to the right. So the binary point is moving, and it's representing more or less bits stored as a fractional component, and this is known as floating point binary. So the big advantage of this approach is that just by using 8 bits, we can increase the size of the number, if that's what we require, or we can increase the accuracy of the number, if that's what we require. And it depends on the number that you want to store as to where the binary point is actually going to sit within those 8 bits of storage. Now, it may not have escaped your attention that the extra problem this creates is we now need to store where the binary point is on the number line in addition to the number that we want to store. This is done by splitting the 8 bits into 2 parts, one called the mantissa, the actual number that you want to store, and an exponent, the position of the binary point in the number. Let's have a look at an example. So here's a typical number in floating point binary. We've got a mantissa of 0, 1, 1, 0, 0 and an exponent of 0, 1, 1. So to convert this number back into denary, we have to firstly look at the exponent because that tells us where the binary point is actually going to be in the number. Note that it starts after the most significant bit in the mantissa, but that's not where it ends. So here we go, let's convert the exponent. Note the most significant bit in the exponent is representing -4 because it's always stored in 2's complement. So there's no -4s, but we have got a 2 and we have got a 1. So therefore the exponent is 3. Now what this means is the binary point has to move 3 places to the right. It's to the right because the 3 is a positive number, +3. 3 places to the right. So that's 1, 2, 3. So our binary point ends up here. So we've now got 0, 1, 1, 0, followed by the binary point 0. So we need to just convert this back into denary now. So remember, this is representing a half, this is representing 1, 2, 4, -8. So we've got 4 plus 2 equals 6. This is actually the number 6. So let's consider another example. Here we've got an exponent of 1, which means the binary point needs to move 1 place to the right, so it ends up here. So that gives us the number 0, 1, with the binary point 1, 1, 0. Now you must note that the exponent does not form part of the number. That's a mistake that some students make. So let's convert this number now back into denary. So we know this is a half, this is a quarter, this is 1, and this is -2. So we've now got 1 plus a half plus a quarter, which equals 1 and 3/4. Let's look at one more example with a negative exponent. So here we've got -4 plus 2 is going to equal -2. So that means the binary point is going to have to move to the left because the exponent is a negative number. So let's draw that out on the number line. So we've got 0, 0, 0, 1, 0, 0, 0. And our binary point started here. But it's going to move 2 places to the left. So now we're in a position where that represents -1. That's a half, that's a quarter, and that's an eighth. So this number is actually 1/8 in binary. Now you may also notice that we had to backfill a couple of zeros over here in order to make the number work. Now there's no problem with that because numerically the zeros are just not significant. So if the number starts with a 0 because it's positive, you can fill with zeros. If the number starts with a 1 because it's negative, just fill with 1s.